I welcome you all in the sixth lecture of stoichiometry and process calculation for chemical engineers. So, in the previous lecture, I have already started the discussion about the fundamental concept of the stoichiometry, where I discussed about how to calculate the, molecular weight, number of moles, equivalent weight, and factor, and various another topic like how to calculate the mass fraction or a weight fraction. And then I have also talked about the weight percent. So, in today's lecture, I will be talking about the mass ratio, that is the third part of the concentration, that is mass ratio. So when we talk about, let's say you have a mixture of two component, I'm just discussing about the binary component system here only, right? So you have two component, a plus b, and if you have a molar mass of mass of a is ma and mass of b is mb, and if you want to calculate mass ratio of a, that is equals to ma divided by mb, and then similarly you can write mass ratio of b, that will be equals to mb by ma, and that can be also applicable for multi-component system also, but most probably in our chemical engineering syllabus we have to calculate for two component, that is easy. Now next thing that I'm going to discuss here is calculating the moisture content based on the dry basis and wet basis. It's also very important concept and very preliminary concept. Right, dry basis and wet basis. So I mean the application of this particular concept is very common in drawing, food engineering or chemical engineering or material science engineering. And when we talk about the weight basis, so weight basis basically express moisture as a percentage of total weight of weight material. So first I'll talk about weight basis, right? So in weight basis, basically it expresses the moisture as percentage of total weight material, right? So that means what you have to understand, if I want to calculate the total mass, let's say total mass will be equals to mass of water plus obviously dry solid, right? And then it is water, mass of water plus dry solid, and then that will make a wet solid. So if you want to calculate moisture based on weight basis, moisture based on weight basis, that can be equals to mass of water, right, divided by mass of wet material multiplied with 100, and that will give you the percentage moisture content. Is that clear? So if you have to calculate the percentage moisture content based on the weight basis, so you will be calculating, and the total mass is this total mass is called as the mass of weight material, right? So this is called as the mass of weight material, right? So what I have told you, mass of wet material, mass of equal to mass of obviously water plus mass of dry solid. That will give you the mass of wet material. Right. So let's say, as for example, if I am telling you mass of water is yours, let's say 25 gram, and mass of dry solid is 100 gram, and if I tell you to calculate percentage moisture content based on wet solid, so that will be equals to water divided by water plus dry solid, and this formula already I have discussed, and that is equals to 25 divided by 25 plus obviously 100 and into 100%, and that will be equals to 25 divided by 125 into 100. So that will give you answer of 20%, right? So this is the moisture content that will you have calculated based on the wet basis. Okay, I hope this is clear to all of you. Now coming to the next point, that is the moisture content based on the dry basis. It's also very important concept. So when I calculate the moisture content, percentage of moisture content based on the dry basis, right, that will be equals to what? Mass of water divided by mass of dry solid into 100%, right? So if I give you an example of, let's say in previous example we took mass of water was obviously your 25 gram, and mass of dry solid was how much? 100 gram. So if I calculate the percentage moisture here, that I'll tell you based on dry basis, that will be equals to 25 divided by 25 plus, sorry, it will be 100 here only in the denominator, into 100%. So here it will get cancelled out, so that will give you an answer of 25%. So if you calculate the moisture content based on the dry basis, it is 25%, and if you calculate the moisture content weight on based on the wet basis, it is 20%. So that means the moisture content calculated by dry basis is more than the moisture content calculated by wet basis, and this is something that is very important that you should understand. Okay, now let's take one simple example. It's very important to understand this concept very deeply. So I am giving you a simple example: a stock of aluminum sulfate a wet stock of aluminum sulfate contain 20% water on dry basis is sent to dryer. The material leaving the dryer contains 2.5% moisture on dry basis. So you have to determine the percentage of water removed in drying operation, right? This is very important concept. I think this question has been asked in GATE also, so it's very important to understand this thing. So let's try to understand these things. You have a dryer, and then what happens? A wet stock is being fed over here, and it is coming out of the dryer. So this is your dryer. So wet stock of aluminum sulfate contains 20% water based on the dry basis, right? 20%. So let's try to understand. Total feed I am sending is, let's say, 100 kg, right? And that contain 20% water on dry basis, right? So if I calculate percentage moisture on dry basis, that is equals to weight of water divided by weight of dry solid, right? And it is I mean, if you see here, it is 20%, right? It is given as a 20%. So I'll tell you, it is 0.20, that is equals to weight of water divided by weight of dry solid. Is that clear? Now, so what you can say here, that weight of water, that is equals to 0.2 multiplied with weight of dry solid. So total weight is 100 kg. So what will happen? 100 will be equals to water plus obviously dry solid. So that is 100, that is equals to 0.2 into dry solid plus let's say your dry solid. So what will be the weight of dry solid here? Solid will be equals to 100 divided by 1.2. Is that clear? And then what is weight of water? 0.20 into 100 divided by 1.2. Is that clear? So if you'll do the calculation, that is 6, that is 100 divided by 6 kg. Okay, that will be equals to 50 by 3 kg, right? So at the inlet condition now, you know, at the inlet condition there is dry solid, and then the water will be there in the dry solid. So dry solid is having 100 by 1.2 kg, and it is equals to 50 by 3 kg. Now here it is it has been given that how much water is being removed, right? So whenever a solid is being dried, the weight of solid will be remain as it is not going to change. So water will be coming out, right? The content of water will decrease. So here what you will see, that dry solid will remain as it is, that is 100 by 1.2 kg, right? 100 by 1.2 kg. And then the material leaving the dryer contains 2.5% moisture on the dry basis. So here the water content that you are getting, that is equals to 2.5% based on the dry basis. Is that clear? So what you can say here, that is 0.025, that is equals to weight of water at exit divided by weight of dry solid, and that is equals to 100 by 1.2. So what is the weight of dry solid here at exit? Sorry, water at exit, that is equals to 0.025 into 100 divided by 1.2 kg. So how much mass of water that is being removed? So let's say water entering was here, we have calculated. Water leaving we have calculated, and how much water is leaving. If so, you can calculate mass of moisture removed, that is equals to W1 minus W2. What is W1? That is your 50 by 3. W1 is equals to 50 by 3 minus 0.025 into how much? 100 by 1.2. kg. Is that clear? So this is something that you can calculate. Okay. Okay, that's great. Now moving towards the next concept, that calculation of mole fraction and mole percent. How do we calculate the mole fraction? So let's say I will be talking about the binary component system. Let's say there are two component. This one is red one, let's say, and then there will be green one. So red one is A and green one is your B. Sorry. And if I am calculating, this is MA and weight is WB. B's molecular weight is your MB and weight is WB. Right. So MA is molecular weight of component A. MB is the molecular weight of component B. WA is component A So what is number of moles of A? Na is equals to Ma by Wa, and obviously Nb equals to Mb by Wb. So what will be the mole fraction? So let's say Xa, that will be equals to your Na, number of moles of A, divided by number of moles of A plus number of moles of B, and the value of Xb, that will be equals to number of moles of B divided by number of moles of A plus number of moles of B. Is that clear? So if we have any component system, then we can calculate Xi equals to Ni divided by summation of Ni, where I equals to 1:n. Is that clear? Where Na is the number of moles of A and B is the number of moles of B. And if you do Xa plus Xb, that will be equals to 1. That means summation of mole fraction of ith component in a particular mixture of substance, that will be equals to 1. Right? And this is the mole fraction. Okay. Now coming to the next thing, that is the another expression for the concentration. It's also very important concept. Right. So when we talk about a solution, that is a homogeneous medium of either gas, liquid or solid, and that is made up of two or more than two components. So in process calculation, basically the term solution is generally used for the liquid and gases, that is made up of solute and solvent. So if I am talking about solution, that is made up of two components, that is solute and solvent. Is that clear? So the component that is present in a smaller quantity, that is called as a solute. So usually this is how you can differentiate between the solute and solvent, and it will be present in the comparative larger quantity. Okay, that's great. So in addition to different method of expressing composition, as we have already studied earlier, so the concentration of solute in a solution can be expressed as parts per million, molarity, normality and all. So here I will be talking about when we have a solution which is made up of solute and solvent, and then how we can calculate the concentration, and how can you basically quantitatively tell what is the concentration of solute in the solution. So let's say this is solvent, and then if you are adding a solute here, so this is your solvent, solute, and then this will be called as the solution. So solution will be made up of solute plus solvent. So the fundamental difference between the solute and solvent is the component which is present in the lesser quantity, that is called the solute, and the component which is present in the larger quantity, that is called as the solvent. Now, first concentration term that I am going to discuss over here is molarity, that I'll denote it as a capital M, and this is the standard notation of molarity. So molarity of a particular solution can be defined as the moles of solute, number of moles of solute divided by volume of solution in liter. Is that clear? So molarity can be defined as number of moles of A divided by volume of solution in liter, where A is the solute, let's say, right? This is the molarity. So sometimes what you can see here, that what is number of moles of A, that is equals to weight of A divided by molecular weight of A, where WA is the weight of solute and MA is the molecular weight of solute. This is something you should know, and this is how we define the molarity. The next term that we are going to study here is the molality. I'll denote it as a small m. The value of molality or definition of molality, that is equals to number of moles of solute divided by weight of solvent in kg. If it is given in gram, you have to convert in kg. That is very important thing, right? That is something that you should know. So the molality can be defined as weight of solute divided by molecular weight of solute divided by weight of solvent in kg. So let's say if I assume you are making a solution, and which is made up of component A, which is your solute, and this is another component V, which is called as the solvent, and while mixing these two you are getting a solution, and this is called as the solution. So the molality can be defined as weight of A divided by molecular weight of A divided by weight of B in kg. So always don't forget these things to convert weight of B in kg. If it is given in the gram, if WB is given in the gram, then convert gram into kg. This is the most important point. Sometimes a student forget to convert these things and they end up doing some mistakes. Now, third concentration definition that I can tell you here is normality. I'll denote it as capital N. So normality is, definition of normality is similar like to molarity, but let's see how we can define. So that is equals to number of gram equivalent of solute divided by volume of solution in liter. Is that clear? So let's say you have a solution here. Let's say A is the solute, B is the solvent, and then it will constitute a solution, right? So now how to calculate number of gram equivalent of solute? That can be defined as weight divided by equivalent weight. Then there comes a how to define the equivalent weight. Already I have discussed these things in my earlier lecture. That is equals to divided by valency factor or n factor, right? So let's try to understand the normality. So now I can define n, that is equals to number of gram equivalent of solute. So I can say that weight divided by molecular weight divided by valency factor, is that clear, and divided by volume of solution in liter, is that clear? Weight divided by molecular weight into volume of solution in liter. So if I write these things, and that can be defined as weight divided by molecular weight, and that will be multiplied with valency factor divided by volume of solution in liter. And what is weight divided by molecular weight? That is number of moles. So n will be equals to number of moles divided by volume of solution in liter, and then that will be multiplied with valency factor. And what is number of moles by volume? That is molarity. So normality will be equals to molarity multiplied with valency factor. So I can write Vf is equals to valency factor or n factor, and n factor already I have discussed in my previous lecture. Is that clear? So sometimes what happens, if you have a normality, that will be equals to molarity multiplied with valency factor, right? And you just see my lecture number 4 where I have discussed about how to calculate the valency factor, and then it will be very easy for you to calculate the normality as well. Okay, so I hope this is clear to all of you how we calculate basically the normality, molarity and all. Now coming to the next concentration term and the last one, that is your parts per million. This is also defined as in written as in the ppm. So the 1 ppm can be written as 1 gram divided by 10 to the power 6 gram of solution. This is very important thing to happen. That can be also written as 1 gram divided by 10 to the power 6 ml of solution if you are dealing with the liquid. Is that clear? Or it can be also written as 1 mg divided by 10 to the power 3 ml of solution. So that is basically your mg per liter, right? So parts per million, that is parts per million is equals to your mg per liter. Okay, so this is all about the concentration term, and in the next lecture I will be discussing one numerical based on calculation of all these concentration term, and then after I'll move forward to the subsequent topic, and where I'll be talking about the chemical reaction and process calculation, where I'll discuss about the excess reagent, limiting reagent for a particular chemical reaction, and then I'll discuss about the conversion, yield and selectivity, and then extent of reaction. So I hope this lecture will help. This lecture will be helping for you to understand some fundamental concept. So stay tuned. See you in the next lecture. Thank you.